You are here because you have shown interest in OFDM and its technology. In this presentation, we're going to rethink the mathematical basis of OFDM. We will offer evidence that the OFDM data rates can be improved by a factor of at least 2 with little change in transmitter hardware. OFDM is arguably the most significant technology of the 21st century because it is the enabler of all high-speed digital communications. And because of this, OFDM may be the most heavily researched technology on a global basis over the last 50 years. The key to our new approach will be replacing the FFT at the receiver to achieve faster symbol demodulation without sacrificing the graceful degradation of the current OFDM implementations. We will also rethink the cyclical prefix, the channel equalization methods, and the receiver frequency synchronization. We do not propose tweaks of OFDM mechanizations, but a new way of looking at sending data across a channel. We're not communication specialists, so our terminology and understanding of the basic technologies may be suspect. Therefore, we have interest in partnering with a communication specialist or firm. Please contact us by email or telephone if you have further interest after hearing what we have to say here. Similarly, contact us with any errors in our presentation and any other analysis and simulation that you would like to see. We will cover a lot of ground in this material, so let's do a quick summary. We'll first go over the traditional OFDM mechanizations and concepts. Our strategy will be to motivate the new approach by showing that it resolves some constraints that are imposed by the traditional approach. We will introduce a new differential equation representation of an oscillating wave that will allow more flexibility than the more traditional exponential notation representation that is used by the FFT algorithm. Next, we will introduce the QAM-modulated single carrier as a stepping stone to the multi-carrier model. And we will show how the new approach works well with the widely accepted QAM modulation scheme. Then we will extend the single carrier system to a 2-carrier system with both carriers closely spaced and modulated with QAM. We will see that orthogonality of the 2 waveforms is not a factor in subcarrier separation. Finally, we will increase the subcarriers from 1 carrier to 64 subcarriers to show the straightforward extension to a practical 802.11 waveform. This final section will also introduce the radio implementations where we increase the data rate by a factor of 2. A few conclusions. We have shown that the OFDM symbol time can be reduced by a factor of 2 when we replace the FFT with an optimal estimator. We will provide a data rate improvement of a factor of 2 if we disregard the requirements for the guard time. This data rate increase was the primary goal for this presentation of the new approach. In summary, we have replaced the FFT processing in the receiver in order to remove symbol time constraints that were imposed by the FFT. We also have enabled both an arbitrary frequency plan layout for the subcarriers and arbitrary digital sampling plan, both of which were constrained by the selection of the FFT. Subsampling of the carrier is offered from the new approach as a means of implementing an SDR radio. Key outstanding issues that must be addressed are numerical implementation of the new method and practicality of RF subsampling. We have also discussed multi-carrier mechanizations that use only a real output from the transmitter rather than the real and imaginary time histories as with OFDM. For such a real information signal, can we use OFDM's IQ mixer for a second completely independent information signal, which would in fact be another way of achieving a 2x data rate?